Okay, so now we're talking about electrophilic additions. So let's see here. Question number one is a question I wanted to take a look at. It's this guy right here. It just says, what's the major product for the reaction shown? We have an alkene, beautiful alkene. We're adding water and acid. This is an unsymmetrical alkene. So is this addition going to proceed with Markovnikov or anti-Markovnikov regioselectivity? Could anybody tell me? And it's not trying to fool you or anything like that? Just taking this alkene right here, treating it with water and acid. So anti-Markovnikov addition across a double bond has to be done using hydroboration oxidation, right? So if we want to do anti-Markovnikov addition, anti-Markovnikov addition is done using borane and THF, followed by hydrogen peroxide and sodium hydroxide. Right, so this is just going to be a straight ahead Markovnikov addition. So if we have our hydronium, right, because we're mixing water and acid, that means we have hydronium, the reaction mixture, which is going to act as our acid. So we're going to get a proton transfer. The rich are going to get richer, like this, and then we would end up with this carbocation. So we end up with this guy, where we have an ethyl group, and then we have a carbocation here. Then water can come in and act as a nucleophile, like this. So water can come in. Maybe I should draw my curved arrow a little better, like that. And then after a proton transfer, we're going to end up with this, where we have an ethyl group and a hydroxyl, which is B. So it's just a straight ahead Markovnikov addition. No carbocation rearrangement. So Markovnikov addition of water across a double bond. All right, let's try question number two, which deals with hydroboration oxidation. Something that I would have told you earlier on in the class is when we looked at borane THF, sometimes we use B2H6 as a substitute. So B2H6 does the exact same thing as borane THF. So we've already discussed that this is going to give us anti-Markovnikov addition of water across this double bond, right? So this carbon is the one that's richer in hydrogen, so that's the one that's going to take the hydroxyl. So that means the hydroxyl should end up here or here, right? It would not end up here, and you would not end up with a diol. So we can scratch off C and D. Could anybody tell me, because A and B are both the product of anti-Markovnikov addition of water, but only one of them is correct. Could anybody tell me which one is the correct one? Would it be A or B? Yeah, exactly, Edwin. It's going to be A. Why? Because anti-Markovnikov addition occurs in a syn fashion, right? This is syn addition of the hydrogen and the hydroxyl. They're added to the same face of the molecule. Again, this is syn, and over here, they're anti. And so the only possible answer is A, is the best answer. It's anti-Markovnikov, and it's the result of syn addition because the hydrogen and the hydroxyl are added to the same face of the molecule. Let's move on to question number three. It says, which would be the best method to carry out this transformation? So we have, what do we have here? We've got 1, 2, 3, 4. We've got 4-methyl, no, sorry, we've got 3-methyl-1-butene. And we're taking that and we're treating it with something, and we're doing just a straight ahead Markovnikov addition. So this is a Markovnikov addition of water across the double bond, right? This carbon is the one richer in hydrogen, so it's becoming richer. So could anybody tell me which one of these would be the best option? just doing a straight ahead Markovnikov addition. Okay, we got some answers here. Most people are answering A. Well, A is a Markovnikov addition. Okay, so this is Markovnikov addition conditions. C is anti-Markovnikov, so that's impossible. So we can scratch this one out. B is anti-Markovnikov addition of HBr, right? So this is wrong too. This is anti-Mark of HBr, so that's wrong. But what about D? What's the purpose of D? Could anybody tell me why they threw D in here? What kind of reaction is this, or what does this do? I have number 1, mercuric acetate in water, followed by number 2 would be sodium borohydride. This is oxymercuration, demercuration. What's the purpose of this? Is that it, go ahead.
Sorry, my Teams is lagging really bad.
No
Yeah, I was
problem.
going to say it was the mercuration, demercuration.
Right, because we avoid a carbocation rearrangement. Right, let me show you why you would have to use these conditions as being the correct conditions. Because if you were to try to do this, okay, so let me draw the starting material out here, which is this molecule. I'll just draw it as a bond line structure. This, okay? And if you were to just treat this with hydronium, let's see what you'd end up with. So you do the proton transfer, the rich get richer. Okay, so we would end up with this carbocation. However, this carbocation would undergo a hydride shift, wouldn't it? And when it undergoes that the hydride shift, rather, it gives you a more stable carbocation. Okay, and so then water would come in as a nucleophile on that more stable carbocation, right? Like this. Okay, oops, not like that, like this. There we go. And then after a proton transfer, which I'm going to leave out, you would end up with this compound. Okay, so that's not the right compound. So we have to avoid the carbocation rearrangement. So in order to take this compound, so let me write it out. Sorry, did I put my hydroxyl in the wrong spot? I did. There we go. So we would end up with this compound. Sorry, I had the right compound on the brain. So you end up with this compound, which is the product of the carbocation rearrangement. So in order to avoid that, you have to take your starting material, okay, and you treat it with mercuric acetate in water, followed by sodium borohydride. And what that does is it avoids that carbocation rearrangement, and you just do a straight ahead Markovnikov addition. And so that would be the correct answer, okay, to avoid this happening right here, this carbocation rearrangement. You want to avoid that at all costs because you don't want to get the tertiary alcohol. You want to end up with this secondary alcohol. So oxymercuration, demercuration would be the correct choice. Great. Oops, that's not where I wanted to go. Right here. There we go. Yeah, so that was question number 3. Let's try question number 4. Right. Just says predict the product from the reaction shown below. This is another example where I think it would be best to draw the mechanism. I'll see if I can kind of squeeze it in on the page. I'm not a big fan of doing, but let's just see if we can kind of get the whole thing on here. I think we can. So look, I've got a double bond. It's unsymmetrical. The rich are going to get richer, right? I'm going to protonate the carbon on the end, and that's going to give me this carbocation. So I've got my methine. Then I've got an ethyl group up here. I've got another ethyl group over here. I've got another ethyl group over here, and my carbocation is here. So what's going to happen is I have this proton, which is the one that's in blue, and this is a secondary carbocation, so that's going to undergo a carbocation rearrangement to give me this, where now I've got, draw that a little better, just give me a second here. There we go. Now we've got a tertiary carbocation, which is much more stable. And now the chloride can come in here, act as a nucleophile. And what does that give me? It's going to give me this compound where I've got an ethyl group, another ethyl group, and another ethyl group, and I've got a chlorine, and that is A. Right? You've got your carbon. It's got 1, 2, 3 ethyl groups attached to it, and a chlorine, and that is your final product. Okay? So again, you can see that the ACS is really hung up on carbocation rearrangements. It seems to be one of their favorite subjects to bring up. Let's see here. Let's look at question number 7. And again, you can probably see as we're scrolling through here, some of these questions are, from organic chemistry 2. Hey, I'm going to just throw this out there to my students. Which set of reagents would you use to do this reaction? Take your time, take a peek at it. Yep, absolutely. Sorry, let me scroll down here. Does anybody else have an answer for this one? Or is everybody just agreeing? Right, I think that we can all agree that this is an anti-Markovnikov addition. Yep, absolutely. Anti-Markovnikov addition. So we're going to use step 1. This is B2H6. So B2H6, that's called diborane. It's the exact same thing as using borane and THF. Okay. And then second step is peroxides followed by sodium hydroxide. So just a regular old hydroboration oxidation, which is an anti-Markovnikov addition of water across a double bond. It's the only thing we've got. We've got no other way of doing it. And it works really, really well. All right, what time is it? It's 10:24. Let's try one more question because we covered a lot of ground today. I want to show you one more question, and it's not an easy question. It's question 8. I want to go over this one with you in some detail. It says the addition of bromine to E3-hexene, which is this compound, will give. So it kind of brings the stereochemistry thing back in here, right? We got a meso compound, some enantiomers, 2 meso compounds, 4 stereoisomers. I mean, I would kind of hope, and I don't expect you to know everything, that's impossible, but I would expect you to kind of be able to figure out that you wouldn't end up with 2 meso compounds. And you're adding 2 bromines to each one of these. So there's no way, there's no way you could get 4 stereoisomers. Anyhow, hopefully you would maybe be able to suss that out. So then the question becomes, do I end up with a pair of enantiomers or a meso compound? That's a very, very good question. So let's draw it on a blank sheet of paper. And this is why scratch paper is just so important for exams, especially when you're a chemist. All chemists always have notepads everywhere they go. When I was in industry, I carried basically a scribbler of some sort with me everywhere I went. So we've got this starting material, right? We're starting with the trans alkene, and we're just hitting it with bromine, right? Br2. And if you look at the mechanism of bromination, okay, so we draw the whole Lewis structure out like this, okay? We've got a nucleophilic attack like this. We lose this leaving group, but this lone pair is going to come in here like this. And so what we end up with is the bromonium ion, right? So now you've got this bond. You've got the bromine in the bromonium ion. Okay, put a positive charge here. And now you've got like your proton. This proton here is going towards the back like this, right? This ethyl group here is coming out in the front. So you have your ethyl group. Whereas this ethyl group over here is going in the back. So let's draw that ethyl group. So CH2, CH3 going in the back. And then this proton over here is coming out towards the front in your bromonium ion, like that. So now you've also produced a bromide. Now, where is the bromide going to attack? Right? You got this big old bromine over here. The bromine is a pretty big atom. And so the bromide is going to attack from the opposite face of the molecule of the bromonium ion. So this is called the Ammonium ion, okay? So now we get this coming in, and it's going to attack from the opposite face of the molecule. Now you can see that it's not going to have a preference for either carbon because they're both similar. Okay, so let's just attack here. So then what do we end up with? Okay, let's draw it out carefully. So we crack open that jack in the box, so to speak. So we end up with this bromine, right? This one is this one right here, right? You have the other bromine, which is going to be in the plane, in the plane of the screen. Okay, so we'll put all the, right? That's this one. Okay, so on the carbon of the three-membered ring, the carbon on the left-hand side, it's going to have a hydrogen going in the back. Okay, and it still has the ethyl group coming out in front like this. I'll just write ET for ethyl. On the other carbon, the one on the right, that's part of the three-membered ring, the one that underwent the nucleophilic attack, its ethyl group is going in back like this, okay? And then its proton is coming out here like this. So could anybody tell me, is this a meso compound, yes or no? So what would happen if we rotated this bond, right? So that we put both of the bromines in the plane like this. Then the ethyl group on this side is still where it is, okay? But if we rotate this bromine up to the top, then this ethyl group is going to be coming out in front. So it's going to be like this. And so we end up with a meso compound because there's a plane of symmetry through it like that. There you go. So if you remember, our textbook has many examples of this. The answer is A. You end up with a meso compound. He has many examples in our textbook where, because if you remember, bromination is anti-addition. So anti-addition. And we also learned conditions for dihydroxylation that were syn addition, right? Using osmium tetroxide, a catalytic amount in NMO, and then anti-addition of dihydroxyls, which is MCPBA followed by aqueous acid. So he goes over many questions about that in, I guess it's probably chapter 8. And he'll give you cis and trans alkenes, and he'll say, okay, if you do which one, do you end up with a mixture of enantiomers, or do you end up with a meso compound? So yeah, you have to remember to rotate that bond, because exactly, it might be a knee-jerk reaction to say, well, look, I got a chiral center here and a chiral center, there you go, I end up with two enantiomers. But you got to rotate that bond to double check to make sure it's not a meso compound, which isn't simple, right? Definitely not a simple thing to do. All right, so that, we've covered most of the review already. I just want to show you, let's look at one more. This is too much excitement. Where were we? Am I in the right book? Oh yeah, I think it was question number 11. Where's that? No, not there. Question number 11. And again, you can see a lot of these questions deal with, no, not that one. That's where son of a gun. I think God is trying to tell me something here. Or somebody's trying to tell me something. It's like, put an end to it, Mr. Dion. Sorry, I just wanted to look at maybe one more for fun. Oh, check this out. I thought you guys would find this interesting because I mentioned it to you in the class a few times. But you know how for anti-Markovnikov addition of water across a triple bond, we always used, or I like to use 9-BBN. But I said that you could also use dicyamyl borane. And then I told you that you could also use just R2BH. It's just the R group is something big. So that's what this would be. It's just a cyclohexyl. So this would count as R2BH. So this is just an anti-Markovnikov addition of water across that triple bond. Okay. So what's that going to produce? It's going to produce an enol, right? You'd end up with this. So remember that C6H5 is the same thing as a phenyl. So you'd end up with phenyl, carbon, double bond, and you'd end up with this enol, right? Could anybody tell me what that enol is going to tautomerize to give which one of the compounds here? Would it be A, B, C, or D? And it's not a trick. I'm not trying to fool you. This was covered in chapter 9, the alkynes chapter. Yeah, you guys are faster than me. Exactly. It's going to tautomerize to give you an aldehyde, isn't it? Yeah, it would tautomerize to give you this compound, which is this one right here, an aldehyde. Great. Excellent, excellent work. Excellent. Again, you guys are faster than me. Can we try? Okay, let's try one more. It's too much fun. Look, where did you see this reaction? Water, sulfuric acid, and mercuric sulfate. The only time we ever used mercuric sulfate in this class was to do a Markovnikov addition of water across a triple bond. Right? Only time. So could anybody tell me what would make the most sense out of the answers here? Yeah. Exactly. I think my students are definitely on the right track. But I just want to review one more thing. And I know we covered this quite a bit last week too, when we did chapter 11. But look, if you take D, and that is the right answer, right? When you do a Markovnikov addition of water, you don't end up with a methyl ketone right away, do you? You make an enol, but it's a regioisomer of that methyl ketone. Oh, I can draw a better flat number. There we go. So you end up with this enol, right? And this enol undergoes tautomerization to give you the methyl ketone. You'll see that in organic chemistry too, you learn a really neat reaction with methyl ketones called the Iotoform reaction. It's actually technically called the Haloform reaction, but whatever. Anyhow, you can be the chloroform or bromoform or iodoform. You know, kind of interesting chemistry there, something to look forward to. Let's look at another question. So again, these are kind of questions that you don't cover until organic chemistry too. So you can see why I had to go through this. Okay, pop quiz for my students. Okay, if you're not paying attention, wake up and see if you can try this one. It says, which reagent would be the best one to go from this alkene to this molecule? I'll just throw that out there to my students. Anybody? So if I was to try D, so we never looked at these conditions, osmium tetroxide, okay? But remember, the osmium tetroxide, the only time we ever use osmium in this class was to do this. So if you were to take cyclopentene, treat it with osmium tetroxide, a catalytic amount, and NMO, you would end up with a meso compound. You end up with syn dihydroxylation. Okay? The answer is C, right? If you take cyclohexene and you treat it with MCPBA, which is a peroxy acid, right? This is the same thing as MCPBA. Okay? You form the peroxide. We didn't talk about peroxides a ton because we said, okay, if you were to treat this with aqueous acid in the second step, then you end up with a transdiol. Okay, you'd end up with this plus the enantiomer. But remember, we did go over it many times in class and said you do have to know that the intermediate is an epoxide. So that's the answer, is this one here. For example, this one here, periodic acid, I mean, that's a reagent we never even look at in this class. It actually cleaves the bond, makes alcohols. Again, not even covered in this class, so nothing to worry about there. And let's see. Let's try question number 19. So that's this one here. So this one deals with halohydrin formation, right? Halohydrin formation, right? Because we're taking an unsymmetrical alkene, we're treating it with bromine and water. Does anybody have a suggestion for this one? All right. So if I look, it can't be C because remember, water is going to attack the more hindered carbon, right? So the hydroxyl is going to have to end up on the more substituted carbon, right? That means that C and D are impossible, okay? If you don't follow me, let's go back to a blank document. This one here, no, not there either. And if we have that starting material, so we have this alkene, it's 1-methyl cyclohexene, right? After the bromination is going to form a bromonium ion. So I'm just going to draw it so that it's on the bottom face of the molecule. Okay, like that. And then we have the methyl group pointing up like this. This is our methyl group. Well, when the water comes in and does the nucleophilic attack, remember we went over this, that the water is going to attack from the opposite face of the bromonium ion. So it's attacking from the top face here, right? And we're going to break that bond here, right? Because this carbon is the one that's the most comfortable with the partial positive charge that passes through it as that ring breaks and the nucleophile attacks. And so what we end up with is a 6-membered ring, okay, where we would have the methyl group going down on this carbon. We'd have the hydroxyl group pointing up, and you'd have the bromine going down. So again, the hydroxyl ends up on the most substituted carbon, and it's also anti-addition. Anti-addition. So this is answer B. If you go back to the answer key, which I'm going to try to find here. Oh, where was it? Here we go. If you look at A and B, both of them have the hydroxyl and the bromine on the right carbons, but you see that in A, the problem is that they're on the same face of the molecule, right? This is syn addition, which is wrong. And then this one is anti-addition, which is correct. So the answer is B. So regioselectivity and stereochemistry is both important when we're talking about halohydrin formation.